And so then I'm going to go back to where you'd start from, in a sense, right? So there are 49 time series parameters associated with that flow sheet. The first one just happens to be the A feed flow. And so, and there's 49 other ones you can go in, and we spend all day looking at the data. So I'll just take that one since Dan has kind of focused us on that. And down below here are the different orders. And the first 40 of them were associated with our attempt to take his fault data. And we did some signal processing, and we just created orders, right, using our program here. So that's a separate little discussion. That's how we did it. It was kind of neat. So basically, when you look at it, we would basically show a time series. And the scan rate is once every 3 minutes. It's interesting. Dan and I were talking about this. Depending on the process and the fundamentals, chemistry, physics, and all that, this is relatively slow. We tended to do more like 1 hertz, or in some cases, hundreds of hertz. So it all depends on the specifics, if you will, of process and your process understanding and the capability of the instruments, and a lot of issues that we talk to clients about when we first engage with them. And so I could then click on other orders and bring in those to see what the A feed looks like, across the data set. And I can go up over to 40 as well. And what Dan was showing was, and a lot of times when you start, you have a date-time mode. And in this data set, we found it much more helpful to align all those. And in this case, it's a continuous process, so that's pretty easy to do with order time. In batch processes, there's a lot happening. And we actually get in with the control system, and we come out with event markers. And we align by event markers. So I can't show you that with this particular one, but we do highlight that in the AICHE presentation. But they allow you to then align by process function, and that's pretty important to do. So now I'm looking at several different instances, if you will, of this A feed. And again, bringing in some Six Sigma and some applied math and statistics, you start asking some questions in terms of, what's the normal level and what kind of variability do I normally have? And you can look at that time series and start to think about that, look at the range of data, and start to do some calculations. But, we tend to make that easy for you. So what we've done is we have a whole programming language. And that is kind of free form. If you know the language, you can do all kinds of good stuff. But we provide templates. And so typically looking at those traces, our statistical friends would say, well, you want a measure of the level, the mean level, the average level, and you want some idea of the variability. And so we basically have a template and a system that will allow you to go in. And if you want to do fancy things, there's all kinds of fancy things. They can click and select and come in. But in this case, I just picked 3 things out. One was a robust estimator for the average or mean. The second one was something similar for the standard deviation, the median average deviation. And the other one is the ratio between the two, coefficient of variation or relative standard deviation. So basically, I can click here on any one of the orders, usually starting at the first one. And I can click, and all of a sudden, within a second or two, I get all of these wonderful statistics. So it looped through all of those sensors that you just did, and it calculated the 3, the median, the MAD, and the COV, and it went down and you can say, wow, I've got all that data set now. And if I click on any one of them, I can see what that looks like. And if I want to get fancy, I can go up and calculate the median and bring that in on the chart as well. So I can do all that kind of in a manual mode, and I can then repeat it for order 2, 3, 4, 5, 6, 7. And then the question would be, well, what does that look like over time? And so what we do there is we go to what we call our monitor charts. And what's happened is, in this my local PC, this would have taken about 10 to 15 seconds per order. So in a couple of minutes, I'd have this chart. These are all of the different orders, right? Starting at order number 1, just highlighted because I selected that. 2, 3, 4, 5, all the way through the order. And at the end, I put some of Professor Ricker's problem batches, right, just so we can see. And automatically, we actually did some statistics for you. So we created the limits for this, and we did it for all the other parameters, just like that. So it's very convenient. And given that we had few numbers of data, we have a statistical algorithm that expands the limits until we get enough confidence, and we finally then freeze them over on the right-hand side. So that's kind of a nice, neat little feature. Another one is going to be what I'll show you now, and that's what Dan had talked about. And that is, you can look at a given value that's out, and then immediately come in and compare it to those that are more normal, if you will. And we find this is this is an obvious one from our perspective. It's very easy to find, but the point is I think the point is made that ultimately you can take a look very quickly and distinguish in the time domain that something crazy happened at the 18-minute mark in this case. Right. So I know I'm going to have to skip really quickly because I want to do just a couple other things, and then we can turn it over for questions. We have these guides that we have available, and I showed you an example of that. These are basically built into the file as information files, if you will, and you can do that generically by process and also on the specific parameter. And information could come up that would help someone who was reacting to this, who maybe isn't the engineer on the process. In other words, a technician or an operator. So that's integrated into the system, as is multivariable or machine learning types of algorithms. So I'm going to show you pretty much the same thing, but with a different view. Instead of a control chart of one parameter called the univariate control chart, I'm going to show you an example of a machine learning visualization for basically the same issue. And so this basically is a three-dimensional portrayal of all those 40 batches. And the control is an ellipse, and it's an ellipsoid, is actually the equivalent of the 2 sigma line. It's a 95% confidence limit. And if I showed you your 3, it would enclose all of the data sets, all the data points. All these are the individual points, the orders that we talked about beforehand. And so if I zoom out, I can show you the faults that, there's 6 faults that Professor Ricker had put up there, and there's actually 15, but I didn't want to clear this up too much. This is the one associated with the A-feed, which I've told you before. These 2 are associated with the condenser system problems, and the 3 of these are associated with the reactor. So what we found, and it's described in the patent, is symptoms across many different variables that go to a common root cause all appear, if you will, in the same kind of quadrant of this new space that's part of what we call a principal component analysis, which is reduce the dimensions of that 49 parameters down to, in this case, 3 parameters. And so we can then visualize, again, here is the control. All the batches that are kind of within that control. You can zoom in, and you can get yourself dizzy by looking around and zooming in, zooming out. But these are the faults, if you will, associated with the other batches. And so what I'll do is go into one of those and follow the particular large bars, if you will. We found operators find this very intuitive. And then I can get down to the univariate chart, in this case, the condenser, and I've got the same kind of a presentation where I have an indication of something wrong, and I can click on what I think is the norm. And you can see, again, there's a disturbance, a difference in the time domain. And all I've done in this is taken a couple of simple statistics, used an automatic program to generate that on a lot of data, and immediately I can pick up the faults that the professor had documented, if you will, on that website. So I know my time is out, and so I just wanted to thank you for the opportunity to show you this, and I'll turn it back to Dan for any questions you might have.